Okay, for these we're going to start by, I'll just do it over the side. So I have 3 times natural log, 3 times natural log of, delete that, of 2x minus 5 equals 7. Okay, and so the thing that I want to solve for is x, but I'm just going to solve for ln of 2x first, and then I can take the e of both sides. So first let's start by trying to solve for this ln of 2x. So I'm going to add the 5 over. Okay, 7 plus 5 is 12. Divide by 3. Now I can rewrite this in exponential form. So my base here is e, right? So that means e to the 4th power is equal to 2x. And so then I can divide by 2. So e to the 4th divided by 2. And so this is the exact answer. And I can get a decimal approximation from that from my calculator. And it's 27.299 to 2 decimals, so 0.30. Okay, that's part A. For part B, I have natural log of x plus 3 minus natural log of x minus 1 equals natural log of x. Okay, and so for this one, I can notice that I have 2 natural logs of the same base that are subtracted from one another. And so I have a property of natural logs that I'm going to use. And that property is that if I have the natural log of A minus the natural log of B, that's equal to the natural log of A divided by B. And that's one of my properties of logarithms that I'm going to use. And so if I use that property, I have natural log of, I'm going to do this one divided by that one. So x plus 3 divided by x minus 1. Okay? And then if I take both sides raised to the e power, I can get rid of those natural logs on both sides. And so I end up with x plus 3, so that's a 3, divided by x minus 1 equals x. At this point, it's just algebra. So I can multiply the x minus 1 on both sides. Then I get a quadratic. And I multiply this into both of those. So I end up getting 0 equals x squared minus, when I subtract that x, I get 2x plus 3. Let's see, does that factor? X minus 3, x, no, x minus 3, x minus 1, that doesn't factor. Let's see, does it factor? I don't think it does. Oh yeah, it does. Oh, I got a sign wrong. Okay, hang on. When I subtract that 3 over, it's minus 3. There we go. All right, now it does factor. There we go. X minus 3x plus 1. That gives me x squared plus x minus 3x. That gives me the minus 2x in the middle. And then negative 3 times 1 is minus 3. All right, so that's what I want. So I get x is equal to 3 and x is equal to negative 1. Now, the one thing we have to be careful of when we solve these functions involving logarithms is that the domain is restricted for logarithms. So let's check to make sure that either of those solutions will work. So let's see, if I plug in negative 3 into any of these, I'll have, in this one, let's go back to our original equation. If I plug in 3 into that, natural log of 3 plus 3, that's natural log of 6, that's defined. Natural log of 3 minus 1, that's natural log of 2, that's defined. And natural log of 3 is defined. Okay, now that works. What if I plug in negative 1? Natural log of negative 1 plus 3, that's natural log of 2, that's defined. Natural log of negative 1 minus 1, that's natural log of negative 2. That won't work because natural log is only defined for positive values. And again, natural log of -1 is undefined. So we have to throw out that one. So our only solution is x equals 3. Okay, for the next one, I have 5 times 1.325 to the x equals 17. All right, so the first thing I'm going to do is divide both sides by 5. Okay, and then since my base is kind of something wonky, if the base were e or if the base were 10, then I would know which of those to use. But since the base is not, I'm just going to take the natural log of both sides. Maybe you could use the log base 10 if you want. So I'll take the natural log of both sides. And the reason I did that is because I want to use a property of logs. And I'll put that property of logs up here by this other one. So that's a property of logs. And another one is that if you have natural log of something to some number, that power can come out front. So that's the one I want to use. That's the reason I took the log of both sides, is because I want to take this power and I want to move it down here. So we get x natural log of 1.325 equals natural log of 17/5. Okay, now remember, this whole thing is a number by itself. So what I need to do, and that number is being multiplied by the x. So in order to get x by itself, I just need to divide by that number. And then that's my exact answer. And so I can say my approximate answer is going to be what? So I can plug that all into my calculator. Natural log of 17/5 divided by natural log of 1.325. And I got how many decimals? 2 decimals. 1.348. So I'll say 1.35 if I round to 2. Okay, let's do the next one. I have 6 times 1.2 to the x equals 5 times 1.7 to the x. Okay. Well, all right. Here we can kind of do one thing or the other. So we can either divide both sides by 6 or we can divide both sides by 5. But we can't completely get rid of those numbers in front of the exponential part. So I'm just going to divide both sides by 5, but you could equally reasonably divide both sides by 6 if you want. So just pick one. So I'm going to divide both sides by 5. So I get 6/5 times 1.2x to the x is equal to 1.7 to the x. And what I'm going to use here is I'm going to use one of my properties of logarithms. And so I'll write it up here with all my other properties. And that is this, that if I have natural log of a times b is going to be equal to natural log of a plus natural log of b. Okay, and that's another one of my properties of logs. Okay, and so that's what I'm going to use here, because I'm going to take the natural log of both sides. Okay, and so I'm going to use this one where I break it up, because I have a product here. The 6/5 is multiplied by the 1.2 to the x. So I'm going to have to use that law of logarithms. So natural log of 6/5 plus natural log of 1.2 to the x is equal to natural log of 1.7 to the x. Oh, let's see here. I wrote this kind of funny. There we go. That's what I meant. Okay, and now I'm going to use this property up here where I move those powers down with the property of logs. So I have natural log of 6/5 plus x natural log of 1.2 equals x natural log of 1.7. And now I just have a linear function in x. So I can move all the stuff that has x's in it to one side, and all the stuff that doesn't have x, I'll switch to the other side. So this term I'm going to move to the other side, and this term I'm going to move to that side. So I'm going to move those two terms. So if I do that, I'll have x natural log of 1.2 minus x natural log of 1.7 equals natural log of, negative natural log of 6/5. Okay. And then I can factor the x out. And if you want, you can combine these two into one log using this property here. And if I do that, I'll have x times the natural log of 1.2 divided by 1.7 equals negative natural log of 6/5. Okay, and then I can divide this thing over, because it's just being multiplied by the x, so I can divide that thing over, and I've got my exact answer. So I'm going to have to move over here. So I've got x equals negative natural log of 6/5 divided by natural log of 1.2 divided by 1.7. And if I get a decimal approximation for that, I get 0.5234. So if I round to 2 decimals, that's 0.52. And that's my answer to part D. Okay. So the next one, I have some drug that's being injected into a person's bloodstream. Oops, so let's see if I can erase this. Okay, so a drug is injected into a person's bloodstream. The drug is metabolized, so the quantity diminishes at the continuous rate of 4% per hour. Okay, so that means I'm going to use, since it says continuous there, I'm going to use a model that involves E, and it's diminishing, so it'll be a negative rate. So let's see here. So Q of T is going to be my initial amount, which is 2, e to the negative 4%. So there's my thing. So then it says, by what percent does it decrease during any given hour? So let's figure out what this part is right here. So if I compute e to the 0.04, I'm going to get that Q of T is around the percent to 2 decimals. So let's see. I'm going to get 2 times 1.04081 to the T approximately. So that means that it's going to, whoa, that doesn't make sense. Oh, that should be negative. Okay. All right, now that makes more sense. Okay, so when I did e to the negative 0.04, I got 0.96078. Okay, and so that is my number that I'm multiplying by, but if I do 1 minus that, that'll tell me how much it's diminishing by. So if I do, so this is equal to 2 times 1 minus 0.0392 to the T. So it's diminishing by if I look at this part, it's diminishing by 3.92%. per hour. Okay. And then the person must receive an additional dose of the drug whenever its level has diminished to 0.25 milligrams. When must the person receive the second injection? And so that's telling us our quantity is that, so I just need to solve this equation. So 0.25 equals 2e to the negative 0.04t. Okay, and then I'm going to solve for t. So I'll divide by 2 first of all. So I got 0.125 equals e to the negative 0.04t. And then I can take the natural log of both sides. And this is just going to become, since natural log and e are inverse functions of each other, we just get negative 0.04t. And then I can divide by negative 0.04. So let's see what that is with a decimal approximation. So I got, I accidentally hit E instead of natural logs. So there we go. I got 51.986. So 51.99, and what are the units of T? Hours? Boy, that seems like a long time. Okay, so 0.25. Did I do something wrong? Natural log of 0.125 divided by negative 0.04. Okay, so there you go. If the price of a gallon of milk climbs at a continuous rate of 3% annually, how many years will it take for the price to double? Okay, so I'm looking for doubling time here. So I'm going to erase this stuff over here so we can compute it over here. Okay. So this is my annual rate, so I'm going to use this P equal P naught times 1 plus my rate to the T. So P is equal to, I don't know my initial amount, but I do know that it's going to double. So whatever my initial amount is, I'm going to multiply it by 2 P naught equals P naught times 1.03 to the T. And I want to solve for T here. So first of all, I'll divide both sides by P naught. And so if I do that, I'm going to get 2 equals 1.03 to the T. And then I can take the natural log of both sides. And when I take the natural log, that power of T can come down by this property up here. And then I can divide by the natural log of 1.03. And if I do a decimal approximation of that, I will get 23.449. So 23.45. And the units of that are years. So in 23 years, the price of milk will double. Okay, plutonium-238 has a half-life of 87.7 years. How long will it take a sample to decrease to 20% of its initial mass? Okay, so it gives us a hint here. We want to use that model because we're talking about something kind of natural here, so we'll do a continuous model. And we don't want to round the calculated value of k. Okay. All right, so let's see here. So we'll see f of t equals Okay. So we're going to do so our model here is f of t is equal to 87.7 e to the, I don't know what the rate is, so kt. But I do know that the half-life is 87.7 years. Oh, whoops, that's the half-life. I don't know what the original mass is, actually. Let's see here. So that's not right. So we'll just say that's P naught e to the kt. Okay, so, right, so I don't have any information here to fill in yet. But I do know that the half-life is 87.7 years. So I know that when I get P naught over 2, that's going to be equal to P naught e to the k times t. That's the value of t, 87.7. Okay, so I could divide both sides by P naught. I'm going to get 1/2 is equal to e to the 87.7 k. Okay, so then I can take the natural log of both sides. Equals 87.7 times k, and I can divide by 87. And so I'm getting that k is equal to natural log of 1/2 divided by 87.7. Okay, we're just going to leave the k like that because it says do not round your calculated value of k. Okay, so there we go. And now I want to find the amount when 20% is left. So 0.2 times P naught, so 20% of P naught is equal to P naught e to the, that's the k, t. So the k is natural log of 0.5 divided by 87.7. Okay. So then I can divide by P naughts, so I get 0.2 equals e to the, there's my kt. So k is natural log of 0.5 over 87.7. Okay, and then I could take the natural log of both sides. So natural log of 0.2 is equal to natural log of 0.5 over 87.7 t. So then I can divide by that. So I get t is equal to natural log of 0.2 divided by natural log of 0.5 divided by 87.7. And that's approximately what? Well, it should be greater than 87.7 years, right? So let's see how many years it is. Divided by 0.5 divided by 87.7. So I got 203.63. And we want to round to a whole number. So that's 204 years. Okay. The next one, find the continuous growth or decay rate of that thing, where t is the time in years. Okay, so what I have here is I have something that's in this form, 20 times 0.645 to the t, and I want to write it this way, 20 e to the k t. So in other words, what I want to do is I want to set this equal to that and solve for k. That's what I'm going to do. So 0.645 is equal to e to the k. I can take the natural log of both sides. Natural log of 0.645 is equal to k. And so then I get, so let's say, write your final answer as a percent rounded to 1 decimal. Okay, so if I take natural log of 0.645, I get k is equal to negative 0.4385, and so that is so the decay rate is 43.9%. the continuous decay rate is 43.9%. So saying the word decay there is including that negative. So if I wanted to say it was a continuous growth rate, then I could say it was negative 43.9. But since I'm saying decay rate, then I'm already implying the negative there. So